After setting up our null and alternative hypothesis, then we can go on to setting up our sampling distribution of proportions. And what we want to be sure to do is when we build our sampling distribution, we want to build it around the assumption. So we want it to be based on our null hypothesis being true. So with the wording of a question for a typical hypothesis test, what you'll be given is you'll have enough information to set up your null and alternative hypotheses. So we'll set up our null hypothesis, we'll set up our alternative hypothesis. Now, I'm going to use some notation here that'll be kind of weird, but with the alternative hypothesis, you can choose between 3 values. It'll just depend on the wording. So we'll either try to prove that it's larger than, less than, or not equal to. So you'll have one of those to choose from the alternative. Then the other piece of information that they'll give you is information for a sample statistic. So all of this you'll have at the beginning of the problem, and then from here on out, we kind of use those pieces to see how extreme is that single sample statistic compared to what we're assuming is true. Now, we have these different proportions at play here, and you'll find with this section in general, P comes up a lot here. We have this proportion in our null hypothesis, and this is what we're assuming is true. So we'll have some value for P and some notation that you're going to see come up, and we'll use it in this video here, is that value for P. Sometimes they'll change that notation and call it P with a subscript of 0. That's just representing the proportion from the null hypothesis. So that will have some value from it. The proportion from the null hypothesis. And equivalently, other notation, you'll see Q is going to come up again, and that'll just be 1 minus P. So in terms of proportions, we have this proportion from the null hypothesis, we'll have this proportion from our sample statistic, and then the other spot where P comes up is p-value, but that represents something totally different because that's a probability. So in terms of proportions, we have these 2 values. And what we want to do is build our null hypothesis around our assumption being true so that then we could compare where does P hat land. So what we're going to do in this video is go through step 2 and 3 of our hypothesis test. So step 2 is going to be to check the central limit theorem. So what we'll want to do is check that we have independence and check that we have randomization. Now again, with those, you can assume I'm giving you problems that pass those. And then where we need to show a little bit of work is with the success-failure condition. So when we have our sample statistic, there will also be some sample size that goes with that sample statistic. So when we check success-failure, what we want to do is check, does this sample size work with our assumption? So I'm going to use my notation up here with P subscript 0 to refer to that proportion coming from our null hypothesis, because that value will be different from our sample statistic. In the examples down below here, I'll show you the difference and how to know which value to choose. So for success failure, we're going to take our sample size times that proportion from the null hypothesis. That should be more than or equal to 10. And then take the sample size times 1 minus that proportion. That should also be more than or equal to 10. And we have to pass all 3 of those in order to move forward with the hypothesis test. Now our next piece is going to be to set up our sampling distribution of proportions. So to do that, we need our parameters. So we'll need our mean for the distribution, which that will just be equal to that proportion from the null hypothesis. So we'll center it around the assumption that we're making. And then standard deviation, where we have that standard deviation of P times Q over N. Same idea, it's just that proportion. We need to make sure that's coming from our null hypothesis. Again, the idea being the sampling distribution is all built around that null hypothesis that we're using. Now, another piece that I'm going to include here is that calculation of the test statistic. Again, it's just that this terminology comes up here and there within the work, or it's an alternative method to use. So your test statistic, how I described it in the previous video, is taking that sample statistic minus your mean over your standard deviation, and that absolutely works. What I'm going to show you in the video though is to find the more exact calculation for it, how to plug it in all at once just in case rounding errors give you incorrect solutions. There can be, depending on the numbers, there can be a big difference. But how this would look is in the numerator, so sample proportion minus the mean, well, the mean is that proportion from our null hypothesis. So you take your sample proportion minus that proportion from the null hypothesis divided by our standard deviation, which is just this big square root. So I'll show you how to plug that in all at once into the calculator to get exact answers. Because if you find those first and then just use those values, especially the standard deviation will probably be rounded. So then when you plug in that rounded value there, it can cause a little bit of error. But plugging it in all at once will give you an exact answer. Okay, so let's see how this works. So I'm going to go back to the examples we just looked at in the previous video, setting up the null and alternative hypotheses, but now we're going to do step 2 and 3. So with part A here, with that antacid, I just copied down our null and alternative hypotheses we found in the previous video. So our next step will be to check conditions. Will be good for independence, will be good for randomization. And something I did here is I just kind of made up a sample. So let's say in testing the new drug, they saw 80% of the people felt relief when they used it out of a sample of 100. So I just made up those values so that we'd have some numbers to plug in here. So when we go to check success failure, what we want to do is take that sample size and see how does that work with what we're assuming for our population proportion. So a common mistake here is to multiply those two values together, the sample proportion and n, but really you want to take that sample size and apply it to your null hypothesis. So what we want to do is take sample size times the 0.7 and sample size times 1 minus that value, which is 0.3. So we'll have a 70 and 30, which are both more than or equal to 10. So we're all good for success failure. Now in step 3, we'll set up our mean and standard deviation. For the mean, you just copy what's in your null hypothesis, which in this case would be 0.7. For standard deviation, we're going to take the square root, 0.7 times 0.3 over our sample size of 100. And plugging that into the calculator, that should be a 0.0458. Then if we need a test statistic, and so I'm going to leave a little bit more room here. So we're going to take our sample proportion, and really it's this spot, and when we calculate p-value, this is where our sample proportion comes into play. But you could see that sample statistic, we don't use it in step 1, we don't use it in step 2. If we're doing our test statistic, then it starts to come into play here. So we're going to take our sample statistic of 0.8 minus our mean, or rather our proportion from the null hypothesis, so minus 0.7, and then divided by, and then for short, we could type in that 0.0458, but because of the rounding there, we might get a little bit of error, so that's where I'm going to show you how to plug it in all at once by taking that square root. And then again, I just want to emphasize this, the sample proportion, it only shows up in one spot on this because everything else should be built around the null hypothesis. So let's go to our online calculator. What's nice is that the online calculator can organize it just as we've written it down. So what I'm going to do is split numerator and denominator. And in the numerator, I'll have 0.8 minus 0.7. And then the denominator, I'm going to have my square root. And in that square root, I'm going to have this fraction. In the numerator, I'll have 0.7 times 0.3 and over a sample size of 100. And that'll give me my exact test statistic. Just make sure that things split correctly. If you try to write this out with parentheses, it's very common to make mistakes. Make sure that square root is over the entire denominator there. A good idea would be, if you're watching this video, is bring up your calculator and make sure you can plug it in the same way that I've done here to get the same answer out. All right, so with that, that is a 2.1822. So that would be our test statistic if we needed it. All right, let's look at a few more of these examples. So with the car emissions, now this one actually had the sample data already part of it. In fact, our sample data is right here. They took a sample of 56 cars and 43 met emission standards. So what we could do is find our sample proportion, which would be that 43 out of 56, which is a 0.7679. And then that's coming from a sample size of 56. So we had already set up our null and alternative hypotheses, independence, randomization, success failure. So we want to take that sample size and see how does that work with our null hypothesis. So 56 times 0.8, 56 times 0.2. And when you check these, you can just round these to whole numbers. They don't need to be completely accurate. We just want to make sure they're more than or equal to 10. Which these both are, just barely. This is a pretty small sample size. We almost missed that barrier with that last one landing at 11, but we made it. All right, mean and standard deviation. Mean would be that proportion of 0.8 from the null hypothesis. Standard deviation, 0.8 times 0.2 over our sample size of 56, which would be a 0.0423. Then if we needed our test statistic, we would be taking our sample proportion, 0.7679, minus the mean over that standard deviation of the square root 0.8 times 0.2 over sample size of 56. Just to show you how that plugs in again. Separate numerator, denominator. Have 0.7679 minus 0.8 over, and then the denominator, grab a square root and a fraction within that square root of 0.8 times 0.2 over 56. And that'll be a negative 0.6005. All right, and one last example here. So we have a poverty rate. Again, this one didn't have any sample data, so I just made some stuff up. Let's say from their county, they took a random sample of 300 residents and they found a 12.1% rate. Now, what I tried to do here is show you the different ways the sample proportion could show up. Like in this first example, they gave it as a decimal. So with that, when you have your decimal, you just plug it in as a decimal. With part B, they give it to you in the form of a fraction of giving you a sample size and your x value. So with that, you'd have to create a fraction first and then get the decimal. Here, they're giving a percentage, so just be sure to take that extra step of changing it to decimal form. When we plug into formulas with percentages, the formulas work in a decimal form, not the percentage form. All right, so independence, randomization. With success failure, we're going to take that sample size of 300 and see how that works with our proportion from the null hypothesis, and then 300 times 1 minus that value. And we'll see that's a 44 and a 256, which are both more than or equal to 10. So we're all good to go there. And then with step 3, mean will just be that proportion from the null hypothesis. Standard deviation will have a square root, 0.148 times 0.852 over sample size of 300. And that should give us a standard deviation of 0.0205. And then if we need that test statistic, we'll take our sample proportion, so the 0.121, minus our mean over our standard deviation that we just calculated. But again, it's better to use the exact value. So we plug all that into the calculator, and that should come out to be a negative 1.314. 0.70. All right, so that takes care of steps 2 and 3. When we go into step 4 is where we'll find our p-value, which we'll use. The two ways we could do it is we could use our setup of the sampling distribution and then plug in our sample proportion, or I'll also show the way of using our standard normal curve and working with our z-score.